can start. So let's start. So, good morning, everybody. So today we are gonna start chapter number 2. In this chapter, I'm gonna talk about data and signals. Okay. So in the very beginning, I think you should know the difference between analog and digital, but I'm gonna make a revision on this one or clarify it. So number one, you should understand data or signals can be analog or digital. So data or signals can be analog or digital. For example, what do you mean by data? So data can be text, any written written documents, can be photos, it can be video, it can be voice as well. Okay. So data can be voice as well. So in case of text, the text can be digital, can be ones and zeros. Okay. In case of voice, if you have a mic and then you take my voice and look at the signal, you will see the signal something like that. Okay. So let me first explain the difference between analog and digital. Okay. I think, yeah, this is a very good figure. This signal or data, I'm going to call it analog simply because the values, it can take unlimited number of values, as you see here. So any signal or data that can take unlimited number of values here. You understand what I'm saying? So for example, you have 3, you have 3.001, all values. So you have all numbers here, okay, in a certain range for sure. But in case of digital signal, as you see here, this signal can take only this a finite number of values. Okay, so as you see here, so it can be this value, it can be this value, it can be this value. Also, it can be this value. How many values here? 1, 2, 3, 4. Limited number of values. Okay, so in this case, we call this signal digital, or we call it discrete, whatever you want to call it. Okay. Any question here? You understand the difference between analog and digital and discrete? Okay, very easy. But what I want you to understand, this can be true for signal and also for data. So data can be analog or data can be also digital. Okay. The very easy example for analog data is voice. Voice can be data, right? So in case of voice, if you have a mic, and if you look the signal after the mic, you will see the signal is actually analog. Okay. So again, it depends on if it takes continuous values or it's going to take discrete values to call it analog or digital. Okay. The next thing I want to teach here is actually a signal can be periodic or non-periodic. So what is the difference between, you can tell from the English name, periodic, okay, or non-periodic. So in case of periodic signal, and you may be familiar with some of these signals, there is a small pattern. In case of periodic, as you see, look at this here, periodic signals, okay? There is a pattern, and this pattern is repeated. There is the smallest pattern is repeated. For example, if you look at this signal, you can see this pattern from here to here. And this pattern is repeated. I'm going to repeat it over and over again. Exactly the same pattern. That's why we call it periodic. Is that okay? So a signal is periodic if there is a small pattern or there is a pattern. Because someone can say, okay, I'm going to take it from here. That's why I'm saying the minimum pattern that's repeated. So someone can say, I'm going to take it from here to here. I'm going to consider this pattern and repeat it. No, that's not true. You got what I'm saying? I'm saying the minimum pattern. So it has to be from here to here. So this is the minimum pattern repeated. Okay. So if the signal has a pattern that is exactly repeated, same, everything is the same. Okay, so this signal here is actually identical to this signal. So in this case, we call it periodic signal. Okay, for example, I can give you another example. For example, if you have something like that, Yeah, this is a periodic signal. And what is the pattern that's repeated here? This part. This pattern will repeat it. The minimum pattern will you repeat it. Is that okay? Any questions? That's easy. So again, so you should understand what periodic signal means. So again, there is a pattern that's repeated. In case of non-periodic, or sometimes we call it aperiodic, you know, in some English words, the word a means it's not. Okay, so non-periodic or aperiodic signal, something like that. Here, as you see, again, it can be analog or digital. Again, it can be analog or digital. Here also, even periodic, it can be analog or digital. But here, if you look at this signal, you cannot find a pattern that's repeated. That's why this one is not periodic, okay? If you look at this one here, this is in case of digital signal. Again, you can see a pattern that's repeated. And the pattern is actually this part here. So if you take this part, you can find it, it's just repeated. But here, there is no pattern. You can't find a pattern that is repeated. Any question here? You understand the difference between... So now I explain two things now. You should understand between analog signal and the digital signal. You should understand the difference between them, or discrete signal, whatever you want to call it. The second one is periodic and non-periodic signals. Okay, any questions? It's very important to know, and that's what we are going to see later in details. In data communication, we usually use periodic analog signals, and we use non-periodic digital signals. Okay, so as you will see just shortly, we have data, and these data are going to be carried by the signals, as you will see. So if I have data and I want to transfer the data from one point to another, so it's going to be carried by a signal. Okay, I have to send the signal. The data is in this signal. Okay, as you will see later. So usually, as you will see in this course, data communication, usually we use periodic analog signals and we use non-periodic digital signals, as you will see. Yes. So the signal we are used to transfer the data is going to be periodic in case of analog, or it's going to be non-periodic in case of digital signal. Now I'm going to focus on periodic analog signals. So here, now I'm going to make another definition. So the signal, it can be simple. The signal can be simple, or it can be composite signal. You should understand what is the difference between simple and composite signal. And there is something very interesting here. Okay, so let's see. You can tell from the name, simple. Simple means it's simple, right? So for example, this one here, this signal has only one sine wave. As you see, this signal has only one sine wave. That's why, regardless what is the frequency, regardless of anything, if it is just one sine wave, okay, or cosine, because cosine is just a special case of sine, okay? But anyway, if it's just a sine wave, one sine wave, so in this case we call it simple signal. Is that okay? We have some signals that are not simple, composite. Okay, so what do you mean by composite? I mean, this signal, it doesn't have only one sine wave, but it has a number of sine waves, and you can add them together. Okay, so for example, as you see here, if I have a signal like this one, okay, is this signal periodic? Yes, it is periodic, because you can see here this part is repeated. You can see it. Okay, however, if we do, and this is a very important thing, by the way, so if we decompose this signal, we will find that this signal actually has three sine waves this way. And what do you mean? What do you mean by it has? I mean, if you add the voltage here plus the voltage here, you'll get this value. If you add the voltage here plus the voltage here, you get this value. If you add every time here, if you add the voltage plus voltage, you will get this one. If you add this one plus this one plus this one at the same time, you will get this one. You understand what I'm saying? Very interesting. So, and as you will see, also it was found that all signals, all composite signals are actually are built from sine waves. So I can say the sine wave is actually building block, is a building block for all signals. Very important thing. You got what I'm saying? What I'm saying, there is something we call it Fourier analysis. I'm not sure if you take something like that in math, but there is something we call it Fourier analysis. So Fourier is the name of the person, it's French name, who discovered this. Have you ever heard about Fourier? Okay. So anyway, so what this guy discovered? So what this guy discovered is that any signal is actually is just addition of sine signals. So sine signals are the building blocks, is a building block for all signals. Okay, for example, just to clarify it, for example, any signal, this is simple. So this is simple, just one. Okay, but if I give you this one and you do Fourier analysis, and this Fourier analysis actually is mathematical way, you can actually, I can know this one is actually is just the addition of these sine waves. And these sine waves can have different frequencies, it can have different phases, different amplitudes even. Okay, so any signal, for example, if you have a signal like this one, yeah, this one is actually is just a summation of a number of sine waves. Okay, anyway, so very important, we will use it. Okay, so let's any sine wave. Okay, there are three main factor or parameters we need in any sine wave. Number one, what we call the period. Okay, I told you there is the small pattern. The small pattern is from here to here, right? We agree on that. So this is the pattern that is repeated. This pattern is repeated. Okay. So the time of this pattern, we call it period, and this is in second. Is that okay? This time is, we call it, this is a period, or we call it interval, and this is in second. Is that okay? From here to here, we call it a cycle. You made one cycle. So one cycle means one pattern. So this is a cycle, this is a cycle, this is a cycle. So every pattern, I'm gonna call it a cycle, okay? So number one, you should, if I give you a periodic signal, this is only true for periodic signal. If I give you a periodic signal, the time of the pattern that is repeated is actually, you call it a period, okay? 1 over the period gives you what we call frequency. Frequency 1 over the period. Is that okay? No, cycle just a name. It's not something you can measure. When I say you made a complete cycle, that means if one pattern, you created a pattern. Okay. So frequency is actually 1 over period, and period is actually in seconds. So frequency should be 1 over second, and that's what we call hertz. You are familiar with that. 1 over second is actually hertz. Okay. The other thing also we need here. So number one, for any sine wave, there are three main parameters. Number one, period or frequency. It's exactly the same thing. Same thing means they come from each other. Frequency is 1 over period. Number two, it's actually the amplitude. For example, as you see here, this amplitude here, the value of the amplitude. What else I need in order to draw this signal? What I need? I need three things in order to draw it. Number one, I need the amplitude. I need the period or frequency. Number three, what else I need for any signal to describe this signal? Number three, what we call the phase. Okay, so this phase is gonna tell you. So three things here, guys. Something phase. This phase is gonna tell you the beginning of this signal. So this signal here starts from 0. That's why this one has 0 phase. But this signal can start from here. So here can be the y-axis, can be here. You got what I'm saying? Or it can start from here. So as you will see now. Okay. But anyway, so let's now focus on frequency, period, Always the frequency is 1 over the period. Also, you should understand what is the meaning of frequency. Frequency. You can, again, from the English name, frequency means how many times it's repeated. You get what I'm saying? And that's true because there is another way to measure the frequency. So to calculate the frequency, it's 1 over the period. That's okay. There is another way. What is the other way? Okay. How many cycles we have in 1 second? So if you come here and see, this is 1 second, and you see how many cycles we have, this is also frequency. It's the same thing. Okay. So frequency can be calculated 1 over the period, or it can be calculated by the number of cycles in 1 second. Is that okay? In order also to understand frequency, I can see it like the rate of change with respect to time. What do you mean? I'm going to tell you what I mean here exactly. So what I mean is, if you have a signal that is, this signal is changing very fast. Yeah, so here you have a signal, and this signal actually changing very fast. And you have a signal, but this signal is slow. Okay, so which one has higher rate of change? This one is changing very fast. So that means this one has higher frequencies than this one. You get what I'm saying? So the higher, and it's even, this is consistent with exactly what I explained, what I told you. Frequency is 1 over the period. So in case of high frequency, so the period equal 1 over frequency, or the opposite, or frequency equal 1 over period. Okay. So in case of very high frequency, so actually the period is going to be very small, as you see here. Okay. In other words, high frequency means we are going to complete too many cycles in 1 second. Okay. Any questions? So again, what I said, number one, for any periodic signal, there is something we call it period and something we call it frequency. You should understand what frequency, the meaning of frequency. Frequency can be measured 1 over the period, or it can be measured how many cycles we have in 1 second. How many cycles? Okay. There is another thing also here. We call it the root mean square. Root mean square. I'm going to tell you why we need something like that. So actually here the root mean square here for this signal is actually the big value here, the big value here, the big value equal square root of 2 times root mean square of this signal. In other words, the root mean square is equal the big value divided by 2. Okay, for this signal. So what is the meaning of it? As look at the English sheet, square root of the mean square. So actually what happens here, if we square this signal, so this signal is going to be something like that. If you square it, is that okay? Because this negative parts, when you square them, they become positive. Okay. If you get the average value here is going to be V big square divided by 2. Is that okay? And then root mean square, you are going to get the root of this one. Root mean square, I'm going to get the root of the square of the mean of this signal. The mean is the mean of the square of the signal, which if you calculate it, so here RMS is actually equal VB divided by square root of 2. Okay. Any questions? Yeah, sure. What was that? Amplitude. How big is the amplitude? So in order, any sine wave should have 3 main parameters. Okay, which is the frequency or period, the same thing, because they can be calculated from each other. The peak, the amplitude here, the peak value, and also the phase. Okay. Let's see here. I think this should be very easy. For example, here, if the period is second, okay, so it's going to be 1 second, millisecond. you should be familiar with this convergence of these units. Millisecond. So millisecond is actually 10 to the power of -3 second, or it is actually second divided by 10 to the power 3. It's exactly the same thing. Microsecond. So microsecond is actually 10 to the power -6 second. Okay. Nanosecond, 10 to the power -9 second. Okay. And 1/2 is going to give you hertz. 1/microsecond. So 1, because this is a period, this is a frequency here. Okay. So 1/10 to the power -3 second, which is millisecond, is actually is going to be 10 to the power 3 hertz. So our kilo, 10 to the power 3 hertz, which we call it a kilohertz. So again, let me write it here. So I think this is very easy, right? So when I say 1/millisecond, okay, so we agree 1/second means hertz. Okay, so if the period is in millisecond, 1/millisecond, milli, as I told you, is 10 to the power of -3 second. Is that okay? And then I can move this one from here to here. So it's going to be exactly 10 to the power 3 second. 1/second is actually hertz. So this one is actually 10 to the power 3 times 1/second. Okay, 1/second hertz. So it's 10 to the power 3 hertz, or kilohertz. Is that okay? Same thing. I'm going to repeat the same thing, but instead of micro, instead of milli, I'm going to use micro. Exactly same thing. So in case of micro here, if the period is 1/microsecond, that means it's 1 to the power 10 to the power -6 second. Is that okay? And then should equal, I can multiply, or I can get this one here. So it's going to be 10 to the power 6 over a second. And as you know, 1/second is actually hertz. So it's 10 to the power 6 hertz. And 10 to the power 6, I'm going to call it megahertz. Okay, guys, any questions? Okay.
Also regarding RMS, it's equal.
Yes. Yeah. So if we're gonna have an example here. Okay. So an example for the sine wave we use all the time is actually the power. So the electricity at our home is actually sine wave. Okay. I know here the electricity is 220 volt, 220 or 240. Okay. But for example, in the United States, it's 110, between 110 and 120. It's not one value, but it's in this range. So because there are many factors that can change the voltage, okay, or the voltage between these two values. Okay. So actually, so if you look at the signal we have here in our homes, so actually it's going to be, this is the electricity we have, is actually a square wave this way. Okay. And the big value is actually between 155 to 170 volts. But the big value. But we say it's 110 or between 110 and 120. So why is there a difference here? Okay, simply because this number is not the big value. This number is actually the RMS. So they give it us in RMS. So given this RMS, and I already give you the relation between RMS equals the big value divided by square root of 2. Okay. So if you calculate, if using the same thing here, I think here the voltage is 220 to 240. Is that okay? So this is RMS value. So if you multiply it by square root of 2, you are gonna get the big value here. Okay. One more thing. The frequency of the signal here we use in the power is actually 60 hertz. I think here it's 50 hertz. In the United States, it's and Canada, it's 60 hertz. But here it's 50 hertz. Okay. So given the hertz we have, you can actually get the period. So here the interval or the period is actually 1/f, which is 1/60 in case of the 60. here in Qatar, it's 1/50. I guess it's 50. But anyway, so which is equal 0.0166 second. Okay. So I can write it in a different way. What I can do is that I'm gonna very important because to understand how can you do this very simple convergence. Okay, so I can write. This is correct. If you want to keep it this way, it's so correct. But usually we don't make it this way. Okay, there is another way you can make. I want to make it instead of second. I want to make it because it's too small. 0.00 or 0.0166. I want to make it in millisecond. Okay, so how can you do it? I'm going to make it very simple. The way you have to do it is if I just replace second with 10 to the power 3 millisecond. Is that true? Yes, it is true. Because actually milli means 10 to the power is -3. So 1 second is actually 1 second is actually 10 to the power 3 millisecond. Also, 1 second is actually 10 to the power 6 microsecond. Why? Milli is 10 to the power of -3, and 10 to the power 3, they are going to cancel each other, so are going to have a second. So what I did here, in order to convert the second to millisecond, I just removed s, the second, and put it here, 10 to the power 3 millisecond. And just I multiplied this one by this value, it becomes now 16.6 millisecond. Any questions? Yeah, sure. I don't know. No, this is different in everything. Okay, even the distance we use miles and foot. Okay, and we don't use liters. We use pound, not kilogram. It's. I think this is how. There is an important point here you should observe. If you go to the United States, you will observe that the wire for the cable here, this wire usually is so thick. The wire is thick. You know why? Because for the same amount of power, because the voltage is small, I need the current has to be high. So the wire has to be thicker. You get what I'm saying? My understanding, I don't know for sure the exact reason, maybe some historical reason, but I think 110 is more safe, okay, than 220. But anyway, even if in Europe they use 220, just different systems. Okay, so here I'll give you just another example. If I give you the period of a signal is 100 millisecond, and then I want to convert this signal to kilohertz, very easy. All what you have to do is that you can say the frequency is actually 1 over the period, which is equal 1 over 100 millisecond. Is that okay? So, and then after that, what you can do is that it's going to be 1 over, so milli here, as you see here, so milli, this milli is actually 10 to the power -3. So 100 millisecond is actually 100 times 10 to the power of -3, which is 10 to the power -1 in seconds. Okay. And then 1 over the period, it should equal these values here. So that means it is 10 hertz. So the frequency now is 10 hertz. Okay. But I'm asking you here to make it in kilohertz. Again, it's a very easy way to do it. So now it is in hertz. So now I'm going to remove this hertz. I'm going to say 1 hertz is actually equal to 10 to the power -3 kilohertz. Why? Because kilo is 10 to the power 3. 10 to the power 3 times 10 to the power -3 is 1. Okay, so they cancel each other. Okay, that's exactly what I did. So just I replaced hertz with 10 to the power of -3 kilohertz. Okay, so this is the result in kilohertz. Yes. You can, but here in this question, we are asking to make it a kilohertz. And sometimes you have to make it in kilohertz because, for example, as we'll see later, if I want to calculate the bandwidth, you should have 2 frequencies and you have to subtract them. So if one of them in kilohertz, the second one has to be in kilohertz. You got what I'm saying? If one of them in hertz, the second one has. So you will need this conversion anyway. That's what I want to say. You got what I'm saying? You need it anyway. So you should be able to convert from kilohertz to hertz, or from here to here and here to here. Okay. And just to make it very easy, as I told you, the way you should do it, if I have hertz, I can say the hertz is actually 10 to the power of minus 3 kilohertz, or is 10 to the power minus 6 megahertz. Is that okay? If it is the other way, it would be easier. For example, or it's the same thing, or easier. So kilohertz is actually, the K is actually 10 to the power 3 hertz. Megahertz, this is when you convert between kilohertz or megahertz to hertz. So this actually is 10 to the power 6 hertz. Okay. Any questions? Okay. So as I told you, for any sine wave, there are three main parameters for any sine wave. Number one, the peak value, the peak value. Number two, the frequency and the period. Okay. Number three is the phase. So now I'm going to tell you what I mean by the phase. Okay. Yeah. So here, the phase means phase describes the position of the signal relative to time zero, at time zero. Okay. For example, as you see here, this signal is going to at time zero start from zero. Okay. But this signal, as you see, this signal at time zero, it's actually is going to be 30. You start from 30. Okay. So here we can know from at time zero, you can know the phase. Okay. You can think about the phase like a shift. Like shift. That's exactly what happened here. So if you look at these two signals, you can see this signal is actually shifted, or we shift this signal. If we shift this signal this way, okay, or if you shift this signal this way, you are going to get the other one. So it's going to be shifted. Okay. So, or at time zero, here I'm going to start from zero. That's why here I'm going to say the phase is zero. So for this one, for this signal, because at time zero, start from zero. So I'm going to see here, here phase is zero. Okay. But here at time zero, it's you 30. You are 30. Okay. So in this case, the phase is 30. Is that okay? So again, what I want to say, very simple. What I want to say, you need to keep in mind, this is the signal. The signal should be this way. The signal has to be this way. Okay. That's totally fine. However, this signal I can shift it right to left or left. Okay. So for example, if I shift it this way, this signal, so it's going to be something like, okay. So shift it this way. So here the phase is zero. Here the phase is going to be this value here. Okay. Or it can be shifted the other way. So for example, it's going to be, instead to start the zero from here, I'm going to start the zero from here. Okay. And it's going to be, okay. So again, if you want to know the phase, you have to look at time zero. Here, there is no shift, or it's zero phase. Here it has some, and this phase we express it in angle. Like this one, the phase is zero degrees, or 10 degrees, 20 degrees, 90 degrees, and so on. Here in this case, we express this phase, as you see here, 30 degrees, okay? So if I write, there is another thing important here, here, this can be time, microsecond, millisecond, time. Is that okay? Or this can be actually angle instead of time, angle. Okay. And to convert the time to angle, for example, if it is, I can say sine t, and t is time. Okay. If I want to convert, what do you mean by angle? Angle means this part here is going to be 180 degrees angle, and this part another 180. So I should go from 0 until 360 as angle. Again, so I can express it in time, or I can express it in angle. Okay. And the conversion will be very easy, as you will see right now. So if I have sine t, so this one, the x-axis is going to be in time. But if I say sine omega t, omega here means 2 pi f. 2 pi f. Is that okay? And if, what is that? F is the frequency. Okay. 1 over f is going to be the period. What I'm saying here, if I want to draw a signal, I can make the x-axis time, or in this case, I can say sine t, or I can make it an angle, okay? And if this angle, that means from here to here, this is 90, and 90, another 90, another 90, another 90. Total angle is going to be 360. So what I'm saying, if I have time and I want to convert it to angle, how I can do it? Very simple. Look, so what I'm going to do, I'm going to say sine omega t. And omega actually 2 pi f. And as you know, 2 pi here, if it is in angle, so actually it's going to be 360. F actually is 1 over the period. So omega d actually is 2 pi f, which is 1 over t times t. It's so that means it's going to be 360 times the ratio of t over t. This uppercase t is actually the period. So here, for example, let me. Okay, so from here to here, this is t, the period. Is that okay? So t over t here, if t is here, so it should be 1. Make sense? 1 times 360, so it's like the ratio. T over t, this t, the time over the period is going to give you the ratio. If ratio from here, the ratio is 1. From here to here, the ratio is half. Okay? From here to here is going to be 1 over 4, and so on. And you multiply this ratio by 360. So that if you are here, the angle is 360. If you are just 1 over 4 here, if the time is here, which is 1 over 4 of the period, so actually the angle will be 90, because it's going to be 360 times 1 over 4. Is that okay, guys? Explain it again? No? It's not clear? Okay, I'm going to explain it again. We agree we can, when I draw a sine wave, okay, we agree I can say sine t. Is this okay? And this is time. And I told you this is the period t, which is 1 over f. And this is the time here. This is the time. Is that okay? All what I'm going to do, I want to convert the time to angle. So that here should be 360. Here should be 90. Here should be 180 as an angle. Here, if you are here, should be 270. Is that okay? To do this conversion, all what you have to do is, I'm going to divide t by the period. For sure, if I'm here, at this moment, is t over t is 1. Because t is the time here, is capital T, is the period here, okay? So here is going to give you 1. Here, if you are here, okay, so this is t over 4. Okay, from here to here is t. From here to here is time t. Okay, at this moment is t divided by 2. Here t divided by 4. Okay, it's a quarter. This one here, this part is a quarter of a period. Okay, if it is a quarter of a period, in this case, if I multiply it by 360, so here all what I'm going to do, I'm going to see the ratio of the time divided by the period. I will see if this ratio is 1, I'm going to multiply by 360, so that here I'm going to get 360. Okay, if the ratio is 1 over 2, here is going to be half. T over t is half, right? Because the time here is going to be in the middle of the period. Half times 360, you are going to get 180. That's why this one will be 180. You get what I'm saying? So all what I did is like I converted time to angle. So sometimes we express the signal in time, or sometimes we express it in angle. Okay. Why the angle is important? Because when we talk about phase, usually we use angle in phase. I am going to say the phase is 0 or 10 degrees, 20 degrees, 80 degrees, and so on. Okay. So if the two signals have the same phase, we call them in phase. So if you have two signals, they have it doesn't need to be 0. Okay. If the two signals have the same phase, we're going to say they are in phase. If the two signals have different phase, so we're going to say these two signals are out of phase. Okay. Also, one of the expression we use, the word lagging. One signal is lagging the other one, or we can say one signal is leading the other one, leading or lagging. Okay. Why lagging or leading? You can see here this one here, for example, here we can say the voltage signal, the current signal is lagging. This is the current here, and this is the voltage. So the current is lagging. Lagging means it's going to be late, start late. Okay, and that's exactly what happens. Okay, so this one is going to start here and this one here. So I can say that when you read something like the current signal is lagging is a voltage signal by 30 degrees. Lagging means it's going to start late, not early. Okay. So what is that? The current is lagging. Okay, lagging. But if you have a signal like something like that, this way, so this signal actually is leading comparing to this signal, leading, because it's going to start early. Okay. One more thing here. Again, this is the reference signal, or this is the signal when the phase is equal to 0. It's going to be something like that. And we write it this way: amplitude sine omega t. Or as I told you, it can be only t in case of time, omega t if it is in angle. Okay. Now I'm going to show you if this signal is shifted to the left or shifted to the right. There will be a phase. The phase is not 0. Again, very simple. Phase means at time 0, I'm not going to start from 0. It already started before the 0, or it's going to start after the 0. That's the meaning of it. Okay. For example, if I shift this signal this way to the left, as you see here, so I shifted it to the left. So what happens here? It has to be omega t plus phi. Okay. But here, if you shift it this way, if you shift it the other way, as you see here, so you're going to start the signal is going to start from here. So actually, in this case, it's going to be omega t minus phi. Okay. So actually, yeah. So this one is omega t. This is you start from 0. When I start from another angle, so I'm going to add or subtract. Okay. I'm confused when I should add, when I should subtract. Very simple. Look here. Look at time 0. At time 0 here. So if you put here t is 0. Okay. The angle here is phi. We are at phi here. At time 0, it's already at phi. Okay. The angle is phi. Here at time 0, the angle at time 0 here, the angle actually is minus phi. Okay. So again, you can know if you shift the signal to the left this way, you are going to add. If you shift it to the right, you can subtract, or as I told you, to make it easy, you can try to think, should I put plus or minus depending on the time at t equals 0. Here the time t equals 0, it is phi, so it has to be plus. It's not negative phi, it's phi. But here at time 0, it's going to be negative phi. Okay, this way. So it has to be, or let me say it in a different way. Here, in order to get 0 here, omega t has to be phi. So phi minus phi is 0. You got what I'm saying? But here, in order to get this 0, so actually omega t here has to be negative phi, because it is going to go in the negative part here. Anyway, I don't want to overcomplicate it, but again, you can see, again, you should understand what the phase means. Okay, so here nothing is here because you start from 0. If you start before it, so it's going to be a plus. If you start after, it's going to be minus. Is that okay? Any questions? Okay. So I told you, how can you convert the time to angle? Okay. Same thing that you can convert to angle or actually to radian. You know what I mean by radians? It's exactly same thing like angle, but the difference is that here, instead of when I say 2 pi, this pi actually 3.14. It is not 1 each. You got what I'm saying? So you are gonna have one example here to understand it. But let's see here. For example, another example here. Here we have two signals here. In this case, I can say V2, this signal is leading V1 by 90 degrees. Leading by 90 degrees, okay? So that's why if I wanna write V1, this signal here, it's gonna be sine omega t. But if I wanna write this signal, it has to be omega t plus 90, okay? Because at time 0, when t is equal to 0, so actually you are here. And here is 90, as I told you. Okay, any questions? And by the way, omega t plus 90, if you look at this signal, that's what we call cosine. Cosine. If you look, you know cosine starts from here. Okay, so cosine is not a new signal. Cosine is the sine, but shifted by 90. If you shift it by 90, so you get it. Okay, you get cosine. Any questions? Again, let me tell you the conclusion, just make it easy. Number one, I told you we have simple periodic sine wave. Simple means it's only one frequency. Is that okay? Yes, one signal. And this signal should have big value. It should have period of frequency. Also, it should have phase. Three things. Okay. Number two, I explained there is something we call it composite signal. And composite signal is actually in signal. Okay. Composite signal means it has a number of sine waves. Okay. So that's why sine wave is like building block for any other signal in the world. Any signal, signal you think about it is actually just addition of sine wave, and there is a way to extract the sine wave of this signal. Okay. Anyway, so let's look at these two signals here. You can see these two signals have the same phase. Why they have the same phase? Because both of them are going to start from the same value. Here they start from 0. It doesn't need to be 0 to be in phase, okay? But here they start from exactly same time. That's why this one in phase, they have the same phase. If you look at the frequency, how I can know they have the same frequency or not? Okay, see, this is the period here, and this is the period here. If the period is equal, if the time here, if this time is equal to this time, and this is the case, so actually they have the same period, and thus they have the same frequency. Is that okay? So last thing, amplitude. If you look here, so these two signals have the same phase, they have the same frequency, but they have different amplitude because this one, as you see, it bigger than this one. Any questions? AM signal, that's a different story. So here I'm just explaining signals. Whatever the signal, why we made it this way by changing the amplitude to make modulation, I don't care about that. We have a signal, okay? This signal, I'm going to describe it in terms of frequency, amplitude, and also phase, okay? So as you see here, this is no shift here. We don't have any shift here. This signal, it is shifted by 1/4 period, because this is period. From here to here is a period, okay? So this is quarter, 1/4, another quarter, another quarter, another quarter. So you can see here, this one shifted by a quarter. And a quarter, when I convert a quarter to, because T is corresponding to 360, as I told you. So the quarter are going to be corresponding to 90 degrees. So either I say it's just a quarter cycle, 1/4 cycle, or 90 degrees. But usually we use degrees with phases, okay? This one here, as you see here, by the way, as I told you, this one is actually cosine, and this is sine, as I told you, okay? We call it cosine. So cosine just a special case of sine, that's it, okay? If you look at this one here, this one, So the signal, you are gonna start from here. So actually it's gonna be shifted by half cycle, because this is half cycle and this is half cycle here. Okay, so it's gonna start half cycle, and half cycle is gonna be 180 degrees, because the complete cycle I'm gonna consider it 360. So half cycle is actually 180 degrees. Okay, as you see here. Any questions? By the way, this signal is just the inversion of the sign. So this signal should be negative sign. So if you compare this signal to this signal, you will find that when this one was positive, this one was negative. When this one was negative, this one was negative. So if this one is sine, this one is cosine. As I told you, this one is actually negative sign. Okay. Any question? Okay, so let's have one more examples here. So these are two signals. They have the same amplitude, they have the same phase, but they have different frequencies. How I can know the two signals have the same frequency or not? From the period. If they have the same period, they have the same frequency. There is another way. Another way, I'm gonna look at 1 second, and I'm gonna see how many times it is repeated in 1 second. So as you see here, it's very clear here. If you look at it's very obvious here, is you don't have the same frequency, because look at the period here. And okay, so it's not, the time is not exactly the same. Okay, so that the time is not exactly the same. Okay, this is one thing. You so here the period is 1/12 second, but this one 1/6 second. Okay, because the frequency is equal 1 over the period. So actually, the higher the period, the lower the frequency. Make sense? Because this one is in the denominator here. Okay, so the higher the period, is going to be lower the frequency, and for sure the opposite. Okay. Also, you can see here this one. If this one, how many we're gonna in 1 second, we're gonna have 12 periods or 12 cycles. 12 cycles here. So this frequency is 12 hertz, but this one is 6 hertz. So 12 hertz means in 1 second we're gonna have 12 cycles. 6 hertz means in 1 second we're gonna have 6 cycles. 1 second we're gonna have 6 cycles. Okay. So if give me 1 second. So here the frequency is divided by 2. Okay, so that means the period also has to be here multiplied by 2. Okay, multiplied by 2. So because when you increase the period, you are going to actually use the frequency. Yes, what's the question here? Oh, sorry, I didn't. Okay, let's move the. I didn't move. Sorry, thanks for. So let's take the attendance quickly. It's 6787. So 6787. Thanks much. Thanks.